Yes, amazing. Okay, let's get started. All right. So last day of class. Just a few reminders. Of course, you know the lab's due now, so if you haven't already, now's a good time to turn your lab in. We're going to do a review session today. I've prepared a review, set of review questions like I've done for all the past exams. I'm going to post the solutions to these as well as the solutions to the optional homework assignments. I'm going to try to have those up tomorrow, but please be patient. It might take me until Monday to get them posted. I promise it'll be no later than Monday. I'm going to do my best to get those up as soon as possible. The final exam is on December 16th from 6 o'clock p.m. to 8 o'clock p.m. So we're going to have a digital logic party, I guess. I don't know. They never asked me what time I want to get final exams. So that's just, it is what it is. So be here at 6 o'clock on that particular date. If you have a conflict, now would be a good time to let me know about that conflict. So send me an email. Please send me an email. If I don't get stuff in writing, then I'm just going to forget about it. So send me an email. Let me know some other way in writing so that I have that and we can sort out a makeup exam time. I'm trying to think of what else I need to talk about. The Zybook stuff's also due, I think, today. So if you haven't finished the Zybook, you have until like tonight, basically, to make sure you've got all the Zybook stuff done, the entire shebang. Chapter 6, basically, right, is what we should be on. And we're going to go over exam stuff in just a little bit. Are there any questions about scheduling things? Yeah.
Yeah, on WebStack, I think it's like really same.
That means here. Yeah, so it'll be here from 6 o'clock to 8 o'clock p.m. And like I said last time, it's not a final exam. It's just an exam. It's worth the same as the other exams. It's only over chapters 5 and 6 from the Zybook. It's not cumulative. So we'll talk about all that stuff in a little bit. Any other questions about scheduling or logistical things before we start reviewing stuff? Awesome. So let's go over what topics we expect to see on this exam. We spent a ton of time doing high-level state machines, just a ridiculous amount of time, like weeks, literally weeks doing high-level state machines. So you can bet there's going to be high-level state machines on the exam. In fact, I'll give you a little studying tip. We spend so much time on high-level state machines that I would venture to say at least 3/4 of the exam is probably going to be over high-level state machines. So if you only have the chance to study one thing between now and December 16th, you should study the crap out of those high-level state machines, because that's going to be the bulk of the exam. There will be some other stuff too. We'll talk about that a little bit, right? So what all goes into a high-level state machine? We're going to talk about some of this stuff in a little bit, right? So you should know what the differences are between those and the regular finite state machine we talked about. You should know how to create a high-level state machine. You should know how to create a data path and what components belong inside of that data path. And then RTL design is just a fancy way of saying how do we design the finite state machine circuit side of the high-level state machine, right? So how do we design the actual state machine part of the high-level state machine? We haven't talked a ton about timing, but you should definitely be aware of the timing issues that are involved. A lot of people ran into timing issues on the final lab, so you might want to review that stuff to get a good idea of what timing issues look like. And then, of course, there wouldn't be an exam for this class if I didn't ask you to write a little bit of VHDL. So you will almost certainly be asked to implement a high-level state machine using VHDL code. You can pretty much count on it. Other than high-level state machine stuff, we spent the last couple weeks talking about some additional components. So carry look-ahead adders we talked about, I guess that was before Thanksgiving. We saw how to do multiplication. We saw how to create register files and ALUs, right, and CPUs, right? That was kind of the topic of the final lab. So this will be, like I said, maybe about 1/4 of the exam, or maybe even less. We really did spend a ton of time talking about high-level state machines, so that's the majority of what I expect to be on the exam. I think this covers all of the topics. I can't think of any other topics that should be on this list, so this should pretty much do it. Are there any questions about what will or will not be on the exam before we do some review questions? Alrighty, let's do some review. Some easy ones to start off with, maybe some conceptual ones, and then we'll try out some some more in-depth examples. So who can tell me some differences between a high-level state machine and a traditional state machine that we've been working with? What are some differences? Yeah. High-level state machine can have variables. That's a huge difference, right? Yeah. What else? What else is different? Yeah.
It can handle multi-bit data values.
So larger data values, absolutely. Either as inputs or outputs or even variables, right? What else? Anything else you would expect to see different? Yeah. Yeah, so we can do variable assignments, we can do like if statements on transitions, stuff like that. So we have a lot more flexibility over what does and does not qualify as a transition between one state and the next. Anything else? Any other differences? I think we got the big ones. We definitely got the major ones. I can't think of any other issues to talk about in regards to that. So what is a data path? You can tell me what a data path is. If you had to define a data path in a sentence, what would you say? I know we spent a lot of time working with data paths, but yeah.
That's part of your episode. You thought you had some circuit. It's part of the circuit for the overall controls your variables.
Yeah, so basically variables, maybe also inputs and outputs, right, as well. So anything that has to do with manipulating variables data, right, that's part of the data path. So what kinds of components do I expect to see in a data path? What kinds of things am I going to see? Yeah?
Like patterns,
Yes. Perfect. So arithmetic operations, all of that stuff that he just said. There's also one other very, very important thing. Yeah. Okay. Comparators, sure. Yeah. What else? Registers, right? So we need registers. What's going to go in those registers? What are we using those registers for? Yeah. Variables, most likely, right? We're going to store variables in registers, and then those registers are going to be fed into those arithmetic operations, the additions, subtractions, shifters, pairs, whatever the case may be. Right? Okay. And so then we've got the data path, that's one part of the circuit. Then we've got the other part of the circuit, right? We've got the actual finite state machine itself. How does that circuit differ from the finite state machines we did for exam 2? What's the big difference between that? So if we think about the finite state machines that we wrote for exam 2, they were kind of self-contained units. This one has to interact with the data path, right? So
yeah, I was going to say the epsilon is like a controller for the data path.
Right.
So like outputs of the epsilon are inputs to the data path, and like outputs of the data path.
Exactly. So they're going to be communicating with one another, right? So the FSM is no longer in charge of everything, right? The data path has some stuff going on over there with all the variables, maybe the inputs and outputs. The finite state machine is just controlling those components. So it decides when to load a register. It decides how a mux should be, the select bit of a mux, right? That's what the finite state machine is going to be doing for us now. All right, cool. Any questions on this stuff? We're going to, of course, create some high-level state machines, at least one, I hope, today. Some more conceptual questions before we get to that. Who can tell me the difference between a carry look-ahead adder and a carry ripple adder? What's the big difference? Yeah.
The main difference with carry ripple has to let the carry bit propagate all the way through each adder, whereas the carry look-ahead precomputes the carry bit for each adder.
Yeah, you nailed it. The carry look-ahead. So the big downside of the carry ripple is we have to actually let that carry bit propagate all the way through. But we did the timings. We've done it at least a few times in this class, right, where we did the timings. So the carry look-ahead adder does not have that issue, right? It's a trade-off. So we know that the carry look-ahead adder is faster because we're pre-computing that carry out bit. But what's the trade-off? What do we have to give up? Yeah.
Transistors. You have to get more logic.
We have a lot more gates involved, right? We have a lot more transistors. That means it's going to be a larger circuit. It's going to take up more space, right? So we're giving up space for speed. It's a common trade-off. I can go faster, but I just need more stuff. Or I can use less stuff, but it's going to take me longer to get the job done, right? It's a pretty common trade-off when talking about circuits. And so you should definitely know how the carry look ahead, or the carry look ahead adder does its thing. We did the example in class. The side book also goes into detail about that. How does a multiplier work? If I pry off the top of the multiplier, what am I going to see in there? What components do I expect to see? Yeah.
Bunch of adders and gates,
Yeah. I think that's it, right? It's just adders and AND gates. So if I give you two 4-bit values and I say multiply these together, how many bits will the result be? Will it be 4? Won't be 4. How many will it be? I think it is 8. Yeah, I think it is 8. We need 8 bits to pull it off, right? We definitely need more bits because 4 bits times 4 bits is going to outgrow those 4 bits very quickly. So it's going to result in a longer vector than what we originally started with. And it works, the multiplier that we looked at works exactly the same way that we were taught how to do multiplication back in, what, 3rd grade or whatever that was, right? Where we just multiply a digit by a row and then scoot over a place and then multiply and then scoot over 2 places and multiply, and then we add it all together. It's the exact same process. It's the exact same process in circuit form. What's a tri-state buffer? What is that? Yeah.
You take, as long as you combine multiple signals into one wire by being controlled to either get IMPs or like value, and as long as you can have it one at a time.
Yeah. We saw this in the last lab, right? I've got an output, maybe from my register file. I want to pick a register and dump the contents out, right? But I want to be able to choose what register that is. So I don't want all of them to be dumped out. I just want one, but that one might be different from one clock cycle to the next. So in order to pull that off, we first get a better marker, and then there we go. We use tri-state buffers for that purpose. So the registers are over here, right? The registers are over here, and then these act as kind of like gatekeepers, basically. If this is on, then I'll allow this data to go through to the bus. If this is off, then the data can't get through. It's blocked, right? It's a roadblock. So you can think of it as like a traffic manager almost. Yeah.
What's the benefit of doing this over a MUX?
Well, it's simpler than a MUX for starters. I mean, this is much simpler than a multiplexer. This is really just a switch. You can think of it almost as a switch, or even a single transistor. Either it's on and it's letting stuff go through, or it's off and nothing goes through, right? It's a good question, though. I mean, it's very similar to a MUX. I think the difference between this and a MUX is always going to be outputting something, right? So if I have a 2-input MUX like this, it's either going to be outputting this or it's going to be outputting this. Whereas a tri-state buffer is either going to output this or it's going to output nothing, like literally nothing. It's blocked off. So that's a little bit different from a MUX, which is always going to output one of these two.
Although the effect of it is still the same as like the effect of a MUX, really.
To some degree, right? We've got 4 values coming in and we're choosing one to come out. Yeah. Yep.
Couple questions. One, is a quote-unquote low signal, how is that different than like if you are?
A low signal.
Like high versus low. Like if I was to have a 0 or a 1 come out of the MUX.
Right. So, oh, I see. So, I get what you're saying. So 0 versus just being blocked off.
Yeah.
So a 0 is an actual value that we care about and can do stuff with. When we say this is off, we say it's actually high impedance, which typically represent that with Z's. In our, if you've ever seen a Z in simulations, I doubt that you have, but maybe some of you have seen a Z in simulations. That stands for high impedance. So what that means is it means that this doesn't have a value. You can think of it as kind of being similar to null, perhaps. You can contrast that with U, which stands for unknown. This maybe does have a value, we just don't know what it is. and then you can have X, which is, this has a value, I don't care what it is. So this doesn't even have a value, it's just void, it's just empty, it's just nothing, right? Yeah. Yeah, it is voltage for sure. Yeah. Yep. Zeros and ones are voltage, so 1 is high voltage, 0 is 0 voltage. Z is the absence of voltage. You can think of Z as being not connected to anything, like a wire that's not hooked up to anything. What voltage does that have? I don't know. It doesn't have anything. It's not hooked up. That's kind of a similar idea to high impedance. Or what if you put like an infinite resistor here, right? That's a way of visualizing high impedance. It just stops it in its tracks. Yeah.
My second question was, how do we know that, like, is there any guarantee that if you have a couple of them like this, that you can't just turn both of them on?
Yeah, so you could turn both of these on, but that would be a bad thing. So what would happen if we turn both of these on, right? So I've got, let's say these are 2-bit registers, and I've got a 0, 1 here and a 1, 0 here. What would the result be if I had both of these on at the same time? I don't know. It'd be garbage, probably be the best way to describe it. So yes, you could have both of these on, but that's a problem. That's a big problem. We want to avoid that problem. What do we use to avoid that problem with the register file? Do you remember? What did the circuit use to avoid turning multiple signals on at a time? How do we avoid that? A decoder. We use a decoder, right? So a decoder is nice for this purpose because we know with a decoder that even though it's got 4 outputs, only one of these is going to be high at any given point in time, right? So we've enforced the tri-state buffers that way. So they work very well together, the decoder and the tri-state buffers.
I mean, I guess that's pretty distributed. I was wondering if it's like, it's on you to figure that out.
It is.
Or if it's like, I should probably stop.
It's on the circuit designer, yeah. The tri-state buffer don't care. Tri-state buffer does whatever you tell it to do. Yep. Yep. Any other questions about this? I thought I saw one other hand. Good. Cool. What's a port? Now be careful because we've seen port show up a couple of different places. I mean port in terms of a register file. What's a port? A register file. Yeah.
Isn't like a combination of like an address and an enable bit and then like the output data?
Yes, exactly. So I have 2 kinds of ports on a register file, reads and writes. So a read port and a write port are slightly different, but mostly the same, right? Where a port is going to consist of an enable, an address, and some kind of data. The biggest difference between a read port and a write port is what? What changes between a read and write out of these 3 things? What changes? Yeah.
Well, when you're reading the data,
I'm sorry?
when you're reading the data,
When you're reading, well, so when it happens, I guess. Yeah. So the timing. Yeah, you're right. But what changes in regards to the ports themselves? Did you have an answer? Or? Yeah. Got it. It's the direction of this. The direction of this value. So for writes, it's going into the register. For reads, it's going out. Otherwise, it's basically the same thing, right? This is pointing to a register. This is saying, am I allowed to do this or not? Right? So really the only difference is the direction that the data is flowing. So these 3 things taken together are a ports. Right? So on your lab that you just turned in, you had probably at least 2 read ports and then 1 write port. Should have done the trick. I saw some people use more read ports, that's fine. Whatever you want. As long as you didn't use 8 read ports, I don't think I like that very much. But, cool. And so then we already kind of did this next one a little bit on the board here. How does a register file work? Well, we kind of went over that with the decoder. So what happens? What's going into this decoder? Which of these values is going into this decoder here? The address is going into the decoder. Enable is also actually technically going into the decoder. So if enable is 1, then the decoder just works as normal. If the enable bit is 0, then the decoder shuts all of these off. Right? It just says nope. right? Shut them all off. So what operation is that for? The decoder is connected to these. So what operation is that for? Well, actually, yeah, reading. But if the decoder is connected to these tri-state buffers, that's a read operation. How do we do the writes then? Yeah. They're connected to the loads of the registers. It's still a decoder though, right? It's still the same process. It's still a decoder, it's just connected to the loads of the registers instead of the tri-state buffers. Right? Cool. All right. Any other questions about register files or the other stuff? All right. So what am I going to find in an ALU? You guys should definitely know this now. What am I going to find in an ALU? What kinds of components? Right off the top of an ALU, what do I see? Yeah. A bunch of muxes and an adder. Yeah, that's usually enough to get a lot of stuff done. You might see some other stuff too, right? For convenience sake, you might see subtractors or shifters or other things, depending on what you want your ALU to do. And the one we did for the lab is pretty simple. Pretty simple. You could have done. I could have asked you to do multiplication, right? I didn't, but I could have. Could have asked you to do division, right? So maybe you see a multiplier or a divider in there. We didn't have enough time to cover dividers, unfortunately, but if you ever get a chance, you should check it out. They're somewhat complicated, but not that bad once you get the hang of it. So yeah, ALU is going to have a bunch of arithmetic stuff and some muxes, and that's really about it, right? Anything else I'm forgetting? Right? So then what do I find in the CPU? I open up your CPU in your computer. What do I find? Yeah. ALU and a register file. That's basically it. Now, there's a lot of other stuff, right? We were talking about a very simplified version of a CPU, but the main stuff, that's what it is. Register file and an ALU, right? That's all a CPU needs to do its job. So, quite literally, the lab that you guys did for the one that you just turned in today, that was a CPU you implemented, right? So the CPUs in your computer are a bit more complex than that, but if you go back 30, 40 years, the CPU we designed would have been actually pretty powerful, pretty sweet. So I know that does us a whole lot of good now, right? But maybe even longer than 40 years ago. 3-bit CPU is probably never particularly useful. Probably one of these 8 to do some larger valued arithmetic. But the principles are the same. If you wanted to change your CPU into an 8-bit CPU, it'd be pretty easy, right? Just go in and extend everything. Pretty easy. So if you wanted to add more operations to your CPU, that'd be pretty easy. Like if I told you to go back in and add in a multiplier and a divider, you'd say, "Hell no, we just finished that lab." I'm not gonna do that. But if you decide to do it anyway, right? You just go into your ALU. You'd have to add in. What would you have to change? What would you have to add into the ALU? What would you have to do to add a couple more operations in? So the muxes would have to get larger, and if the muxes get larger, then what do we have to do to accommodate that? The select bit, which is driven by the opcode. So we need a larger instruction set, right? We only had 8 operations. I could do that with 3 bits, but if I add more than that, then I need more bits. But yeah, I mean, you could do it, right? You can do it. Just make everything a little bit bigger, so you have room to do the stuff. Now your CPU can do more stuff. I'm sorry? Yeah, well, I'm not going to. I'm not going to do that. Cool. Any other questions about ALUs, CPUs, register files, adders, multipliers? Alrighty. I think we've got, yeah, let's do this. Let's create a high-level state machine. So for lab 4, you created a high-level state machine for a stack. Well, a stack was first in, first out. So, I'm sorry, last in, first out. I take that back. So a stack, I put a value on the stack, and then whenever I call pop, it just gives me the most recent thing that I gave it, right? A queue is like a line. Like you go to the bank, you get in the back of the line. Whoever was the first thing that came in is going to be the first thing that goes out. So first come, first serve, right? That's another way to think about it. So You can use your queue as a starting point for this problem. In fact, you should if you have that stuff available. If not, then use your memory to the best of your abilities. Construct a high-level state machine for this queue. And then why don't we just do the first one, right? Let's do the high-level state machine first, and then we'll talk about that, make sure we're all on the same page, and then we'll do the data path and that stuff later. So take a few minutes. Yeah, question?
Do we have, is there a size? So
You can choose the size. Yeah, I don't care about the size. It's arbitrary. Choose whatever you want for the size.
Oh, yes, 1 bit.
1 bit?
1 bit queue.
One bit
Just
queue.
raw haywire. Done.
Got it, I'm already on it. We're on the wire.
Here? Data out will be the next like
Yeah, maybe like a concert. I don't
Yeah, I think so. That's kind of the idea by giving you this problem. That you have something to go off of.
Right.
What'll end up happening is that you won't end up getting there's a more efficient way to do it.
No, they turn off.
Data out of here goes
Well,
you know, because when you remove it. Wait, I get you. I just want to make sure.
Yeah.
If you read and like you, does that work? Or does that look like special?
It should take it out.
Okay.
Because otherwise, you're
Yeah,
going
do whatever
to
change.
fill up really fast. Yep.
Sorry, let me bring up
Whoever's at the finish. Right, the front of the line, like the stack. Yeah. For the queue, it'll be whoever's at the front of the line, right? That's whoever's been there the longest.
Yeah, you have to check out what's the next spot on the line. Oh, the out.
But now I'm saying you can't.
The queue is very different.
Yeah. Queue's pretty different from a stack. It seems similar on its face, but it's actually got.
Yeah, you are shifting. You're shifting.
Yeah.
But then how do you keep track of the last Oh, you like, yeah, like how would you say remove this data? So the counter, so we're gonna put
Oh, I see. You don't shift when you queue.
you're gonna shift
Yeah, but the line,
It just requires a shift.
you don't have fixed number of, like, how you know how to play.
Put a right shift into where? Into the void.
I set the variable and you left shift, but it doesn't tell you what it is.
Okay, so you left the shift. Okay, so you're putting, okay, so you're putting the first thing out in your queue at the high address.
Yes, and then
Okay.
when you DQ, you don't shift.
Yeah, you were just thinking that you're much there, right? There might be a ball, right?
Right. So we don't have
Yeah. Yeah.
The thing is, when you DQ, you just move these points back. So you're basically saying, like, even though there's data here, it's not you don't even actually have to shoot it.
It is basically.
Yeah, that makes more sense to have the first two out.
Right, you just have to make sure you DQ something.
Okay, let's talk about this problem. So we're designing a high-level state machine. What questions should we be asking ourselves about this high-level state machine to help us design? Yeah. What does it need to remember? All right, so what does it need to remember? Who can help me out here? What do we need to remember? I'm sorry? The queue itself, so we need a place to put the stuff that's going to be in the queue, right? So we know we're going to need that. What else do we need to remember? Yeah.
Some sort of how folder queues.
So we need to know where we are in the queue, right? We need to know where the count is in the queue. So at what position are we, right? Anything else we need to remember? No, you think we're good? So then what are our states going to be? The states are also things we need to remember. How many states do we need to pull this off? Yeah.
I was gonna say
Three?
full, empty, and neutral.
Full, empty, and then in between?
Yeah.
Okay. I actually like that idea. I know that some people probably did this perhaps with fewer than that, with one state. In fact, with high-level state machines, that's a common thing to try well, maybe not to try to do, but a common thing that I've seen is that people are cramming everything into one state and then just writing out a whole bunch of code on all the transitions, right? Not technically wrong, but also not the greatest design in the world because you're putting a lot of onus, you're putting a lot of weight on that one state. I think it's better to spread it out a little bit, so I'm going to go with that. I'm going to go with empty, full, and then, I don't know, in between. Yeah, that's fine. Empty, full, and in between. And where are we going to start? We're going to start at empty, right? We're going to start there. And so then let's talk about transitions, right? So from empty, where can I go? I can go to in between, and when do I do that? So once I have, so once I have an NQ signal go high, right, then I'm going to go to in between. So on NQ equals 1, right? I'm going to transfer from empty to in between. Yes? Yes, well, data in, I mean, we're going to assume is going to be, it's up to whoever's using this thing to make sure that data in's got the value, right? So we don't actually care what data in is. The value of data in, whether it's a 0, whether it's a 1, whether it's something different, we don't care what that is. We're just taking it as it comes.
How do I understand, like, if there was nothing,
If there was nothing, I mean, I don't think it could be nothing. It could be something strange like an X, like an undefined, but we can still read that value in and put it in the queue. Right? We'd still be able to queue that up. We don't care what the actual value of data in is. So when NQ is 1, we're going to go hang out here, right, in the in-between state. Right? So then, does anything else need to happen? I don't think, yeah. Yeah, so we need to get the data in and we need to actually stick it in the queue. So what are we going to use to help us with that? We're going to use maybe count, right? Potentially, or we might not need count in this particular case. We just need to put it onto the queue. So we could say, queue at 0 is data in. We know we're at the first. We know we're at the first position, right? Because we're empty. We got nothing. So let's say queue at the first position is data in. Do I need to do anything else? I need to increment count. So count plus plus count. That looks like count. Whatever. Okay. Do we have any other transitions from empty? Any other transitions from empty we need to worry about? I'm sorry? So we got a self loop for sure, right? So we're gonna self loop when NQ is 0. We'll just keep self looping, and we don't have to do anything for that, right? Anything else with the empty state? I think we're
What happens if, theoretically, if someone were to try to NQ and DQ at the same time, it would be empty, right?
Right. So NQ and DQ. That's a good question. What happens if somebody tries to NQ and DQ at the same time when we're empty? Well, I think any kind. I guess it's a little ambiguous, but the way I envision this, and maybe you envision this differently, I'd be interested to hear what your thoughts are. But the way I envision this is, if I'm truly empty, then I can't DQ anything. Even if I take a value in, I have nothing to give you back out yet because I haven't, finished reading this value in yet. That's how I envision it. If you envision it a little bit differently, that's not necessarily wrong. Right? The question was left a little ambiguous in that area. So the way I'm interpreting this problem is I cannot possibly DQ anything from the empty state at all. Right? Even if I NQ something at the same time, I still can't DQ something from this state. It's not going to happen. I have to have at least one thing in my queue in order to DQ it. Okay? You would just ignore it. You just whatever. You just say, I see that you're trying to ask for something, but I don't have anything to give you, so sorry. Right? Just can't do it. Right? What else? Anything else we need to talk about with the empty state? What about in between? So in between, I think is kind of going to have a lot going on. So what do we need to do with in between? Technically, yeah. Self loop where we increment count, and so what condition is that going to be? What's this transition on? NQ equals 1. We're going to read in. So how do we store data in? How does that work? So if NQ goes high, I can't say Q at 0 anymore, because that's probably occupied. So what am I going to say instead? Yeah. Q at count, sure. That should work. Count is data in. Right? Anything else I have to do? Count plus plus, yes. Okay? Right? Well, so yeah, I mean, that's a different question. So when do we transition to full? How do we know when we transition to full? Right, so when count is up to the length of our queue. So we do have a transition from in between to full. I think that would happen in NQ and count equals length minus 1, I guess. Because we're about to, do the queue thing of counts. I'm going to get tired of writing that. And then count plus plus. So now count will be equivalent to the length. That indicates that we're full, correct? Yes?
How does like NQ and count be a number that's...
I'm sorry?
NQ is 0 or 1. How?
Oh, yeah, I meant to say NQ equals 1 here. Sorry. Thank you for pointing that out. Yeah.
And then for the in-between conditions, then do I need to say it's not, count is not
You could explicitly lay that out. I mean, the fact that we have and count is equal to length minus 1 implies that otherwise we would do this. It's implied. If you want to make it explicit, that's fine. No, probably not. No, I wouldn't take points off for that. Okay, so we've got a whole bunch of NQing going on. NQ, NQ, NQ. We haven't taken anything off yet.
Should your transition be in count equals length
Minus 2?
because you're going to be adding something in. So you need one spot left. Zero spots left.
So if length is 16 and count is equal to 15,
You have 0 spots left. If we're starting from 0, we're starting
Well, but if the count,
so I put the thing into position 15, I increase count by 1, and now we're full. Position 15 is the last position that I have. So if count is 15, length is
Okay.
16, count is 15, I put the thing in position 15, which is the last
Okay, yeah.
that I have, and then I increase count by 1.
Yeah, okay. Sorry, you're trying to.
Yeah. I mean, yeah, you could definitely do it a little bit differently.
Yeah.
Absolutely. I agree entirely. Right. What else? What else we got? Any DQ stuff? So we got a lot of DQ that we need to do as well, right? I'm going to have a similar condition to go back to empty. You see that? So if I do this, right, DQ equals 1, and count equals what? 1? Or count equals, yeah, count equals 1. Then we're going to get rid of that thing. How do we get rid of that thing? How do we get rid of the first item on the list? That's an interesting question. Figure that out in the lecture. So we say data out is Q. I'm just going to start abbreviating that because I'm tired of writing it. Count. Yeah, Q0. You could just use Q0 for sure. And then we also need to say count minus minus here to bring it down to say that it's in fact correct. Trying to think. I feel like I'm forgetting something. You have to right shift to Q. Right shift to Q. Well, I guess it depends on where you see the front of the line being. Whether you see it on the right or the left. Although, I might ask you, do we really need to right shift to Q? Does it matter if the old values are in there? Like, say we're done with them. Does it matter if the old values are still in there? It doesn't. Right?
Well, wouldn't it because now you want the new front of the line to be 0 so that it works here?
I'm sorry?
Wouldn't it matter because you want the like if you're doing if you don't shift, then the one currently on the leftmost or rightmost is the old one you got rid of now.
Mm-hmm.
But we reference, for example, Q0 several times, so we'll be referencing the old value. Like every single time you DQ, it's going to be Q0.
Every single time you DQ, it's going to be Q0. Well, you could do it that way, right? I mean, I guess that's two different. There's two different approaches here, right? There's two different ways to think about this problem. That's something that we should. That's something that we should resolve once and for all, so that we are all on the same page. If I have a line of stuff, right? Here's my stuff. We're saying, I mean, where's the front of the line? I've been envisioning this as being the front of the line. So when people get added, we have to scoot stuff over. Or no, I'm doing it the other way, aren't I? I'm saying this is the front of the line, right?
Yeah.
So DQ will always be the first position. You're absolutely right. Yeah. I was getting the two things mixed up. But you could also have it be such that this is always the front of the line and scoot things over as you add things on.
Yeah, so we need to do left shifting on that.
Yeah, so you could do it either way. You could do it either way. I think that's fine, right? I think that's okay. But my question still remains, right? Do we really need to get rid of this old stuff, especially if we're empty?
Yes, because
If count is 0, we're going to say we're
okay,
empty,
if
so
you're-
data out
if
doesn't
you're
matter.
empty, then it doesn't matter.
data out doesn't matter. If we're in between, right, so count is here, right, and let's say we NQ something else, well, what's that mean? That means I'm just going to write a new value in here and then scoot myself over to the next one, right? So in that case, does it really matter that I've got other junk out here? I'm not looking at it.
Yeah,
So where's the end of the line and where's the start of the line?
The way we've got it, this is always the head of the line, the way that it's sketched out right now. So we need to make sure that we're being consistent with that. If this is always the head of the line, then we 100% have to write shift. That's correct.
because your head is always up
Yeah, because this is always the front of the line, so we just have to keep.
here. Yeah. Now you can keep a second variable called front of line.
Yeah, so I think that's, yeah. You could keep a second variable to track where you're at. I think that's actually how I do it in the VHDL, but we'll get to that later if we have time, which we probably won't, but I'll post it later anyway. Okay, so we do have to write shift. I agree. We have to write shift. That's the moral of this story. Anytime we DQ, right, we have to write shift everything, except for possibly the very last one, right? Because if we're empty, then we're empty, and that doesn't matter. Yeah. So any other time we DQ, so there's going to be another thing here for DQing, right? DQ. Let's do this one now since we've been talking about it. What am I doing here? I don't know how to spell DQ anymore. Too many U's and E's. DQ equals 1, right? Then we want to, so data out will be, actually, we'll just shift everything to the right. I mean, Q, U, P, U, E. Shift to the right. It's going to be set to, oh gosh, how do I write this out? Really, data out is just always the first position. So honestly, I'm tempted to just say data out is always Q of 0 if count is greater than 0. Otherwise, it's X. We don't care what it is. It doesn't exist, right? If count greater than 0. Yeah, else X. Well, we only have it here. We only have it there. So this covers it for all cases, right? Data out is Q of 0 if count is greater than 0, else X. Yes? What?
Okay, I'm going to ask, why do you need to shift and remove from the back to the way? Don't you move back from
I don't have the shift here. I purposely did not include the shift here. This is for the self loop, right? If I see it's DQ'd, then shift the Q to the right by 1. That's what this is saying. Yeah. If it's going back to empty, I don't think we need to shift because we're empty. We don't care. It's just done. We're over it, right? We're done. Okay. So we've got NQ, DQ, NQ, DQ. We need a DQ, right? To go back here. So I am quickly running out of space. DQ equals 1. We'll say count minus minus. And we also need to shift again, right? So Q is shifted to the right. Equals, there we go, shifted to the right. I think, are we, oh, did I miss one? This one here, count minus minus, thank you. Yeah, so that was I knew about that one. I was saving that one for last on purpose. So what happens when we NQ and DQ at the same time, right? Well, we're going to do them both. None of them take precedence. They both get it. So what happens when we NQ and DQ at the What do we need to change? Count's ultimately not going to change, right? Yeah, so we just shift everything to the right and put data in at count, and count remains the same because we took one thing off and we put another thing on, so we're all good, right? So I am super duper out of space, but I'll do what I can. Equals 1 and dq. Whatever. I'm getting tired of writing that word, so q at count. Oh no, we need to move count first. Or no, count doesn't change. We need to shift first. Q equal to q shifted to the right, and then q at count is data in. All right. Cool. And if we see an NQ and a DQ happen at the same time, we know that we'll never go to empty or full, right? We know that we can never go to empty, we can never go to full, right? I'm sorry, yeah, because we're not changing count, exactly, because the quantity remains the same before and after. I think this is good. I know it's probably a little messy. I apologize. I should have used more of the whiteboard, but I think this looks good. Are there any questions about this before we try and do? Yes?
Does data out only have a value if something is DQ?
Well, it always needs to have a value. I mean, it can't just disappear. So it's always going to be the value that's at the front of the line, which from our example is always the rightmost bit.
I see. So it just doesn't change.
Sure. Yeah. I'll be honest with you guys, I think the solution that I'm going to post for this problem is a little bit different from this one. So just to give you a heads up on that, I wanted to go off of what you guys suggested. So don't be surprised if you look up the answer key and you see things are a little bit different. That's okay, right? That's all right. There's always going to be multiple ways to accomplish the same thing. It's not a good thing. It's not a bad thing. It's just a thing. So don't worry about that. Just be aware that we're kind of going down a different path here. Not a problem, though. Yeah.
Let's figure out the whole like overriding thing
With empty. So let's say I get down to my very last value, right? Get down to this very last value here, and I say, all right, DQ something for me, right? Pop one more thing off of this Q. What we're saying is it doesn't matter if we shift this to the right, because we know what the value of data out is, and we know everything else because we're in the empty state. So we don't have to worry about shifting this to the right if it's the last item. Because the next thing that's going to come in is just going to be overwritten in this very same spot.
There's like theoretically no spaces, and so they'll take the first space and then.
Yep. Yep.
Then if in between, then it says the data out is Q of 0. It must be a Q of 0 if.
That's correct. Actually, data out in this case should not be Q of 0. Thank you for pointing that out. It should be like X. We don't know what this is because we are now officially empty. Thank you. That was a mistake. When we're empty, data out is just, I don't know. It's nothing. We don't care. It's empty.
Like that condition is the last thing you copy.
Right, but I'm always looking at what's in the front of the line. So when I take the last thing of the line out, there is no more front of the line. Yeah. Just empty space. Yep. Any more questions that I can answer about this before we try and construct? Yes.
In general, is there ever an order to things like that? Let's say we had some weird state in which it's like you, in the course of just a transition, like you add something and took it away, like does the value or whatever it was ever happen? Like let's say you had data add or something like that when you first got it. Let's say that in one transition we have added someone like also in does that ever lift data out at all, or does that not?
Well, data out should change, right? Because the old value is now gone, and whatever that new value is should take its place.
Let's assume, so the way I envisioned this was that if you had an empty line and you had empty and DQ, then someone would walk in and then immediately answer. They wouldn't wait at all.
Yeah.
Then
Well, you could include that here. You could include this case where, but then you're right. I don't think you would see data out at all if that were the case. I think you would just see it as being a standalone.
Gotcha. Even if someone was briefly in that line.
I So, I mean, I'm struggling to think of how you could do it any other way. Yeah, you could have data out remember the last value that was popped. You could do it that way. You need a register, but that's not a hard thing to do, right? Do that. Sure. Any other questions about the style of the state machine? It looks kind of similar to the stack one, but also very different in some ways, right? Very different in some ways. We only have 15 minutes left, but I think that should actually be enough time for us to at least do the data path. And I've got a ton of questions about the data path over the last few weeks, so I'd like to do that problem. So take 5 minutes or 7 minutes maybe, and see if you can construct a data path for this high-level state machine. And then we'll talk about that to wrap up class today. Yeah, we talked about it a little bit before. I think it's not a horrible idea to do that. I think it also depends on the output, because sometimes we have I mean, let me put it this way. I'm never going to have an output, but but on the same like if you're an output, well, no, that's you don't have to get. I mean, it'd be a win and you could, but
They were so shocked. Like when you last got, you don't go to the duck to eat and then go back. You go home. Hopefully. That's going to be me.
Oh yeah, all day. That's all I got. Hold on a minute. Well, so you can do that first, but if you ever actually get
Right, so like, so instead of like throwing a box for count, instead of just like the signal goes. Showing up right there, that's really actually.
just do the label of the name, and then when we construct the MSN drive, okay, let's see if we can take care of this data path real quick before we run out of time today. So, what's the first thing that you're gonna place in your data path? Or at least what's the first thing that I usually place in data path? I think it's good practice. Registers. So how many registers do we need? Yeah, 5. Okay. What are those registers going to be for? The outputs and the things we need to remember. So yeah, the Zybook says we need a register for every output. So we can do that. How many outputs? We've got 3 outputs, right? Data out. What are the other ones? Empty and full. So I guess data out, empty, and full are just single bits. So really just flip-flops, but that's fine. I'm sorry?
We need a whole register for.
So yeah, we talked about this a little bit when we were first doing high-level state machines. The Zybook says, yes, absolutely, you need these for every single output. I will never mark you off if you put down a flip-flop for your outputs. Never count you off for that. I'm of the opinion that it's not necessary absolutely every single time. And we've done some examples in class where I haven't been using flip-flops for the outputs. But we'll go the Zybook way this time. There's no harm in it. There's no harm in doing it this way. So we'll do this for now. I'll call this data out. I'll call this empty. Oh man, I forgot how to write. Empty and full. Okay. Load. And then the other 2 registers are for what? Q and count, right? Q and count. Okay. Excellent. Let's start with the outputs. The outputs are single bits, so that's fairly easy. We're not doing any arithmetic with these, right? Not doing any arithmetic with these whatsoever. So, we've got 2 signals here. We've got a load signal as well as the actual data that's coming in. Where is that stuff going to come from? Any of them. I don't care. Name one and tell me where it's coming from. So, full is, the data out is coming from, this guy, right? Except, the Q, I'm sorry, you're right. The Q, if count is greater than 0, otherwise it's going to be X. So we've actually got 2 choices here. So how do I separate those choices? A mux. We've got a mux here. We've only got 2 choices, so that's not bad. One of those choices is X. The other choice is going to be bit 0 of Q. So I can just take this guy and feed that into my mux. We'll say this is Q0. I'll just label it as such so that we don't have any confusion. What's going to control these guys? I've got the select bit for the mux, and I've also got this load signal on my register. What's going to control those? Yeah. Finite state machine is going to control these, right? The finite state machine controls those signals. All right, so one down. What about empty and full? What's going to go into empty and or full? So we actually haven't included those on our high-level state machine. We neglected to include those, but they're pretty easy. Yeah. Yeah, so we're going to need a comparator with count down here. Actually, I guess a couple of them, perhaps. So if count is equal to the length, whatever the length is, then we want full. Otherwise, right? So let me just put that up like so. Cool. And then we have another comparator for equal to 0, right? With count, and that will be fed into the empty. Right? Like so. What about these load signals? Finite state machine. All right. Those are done. Let's talk about the queue. What operations happen to the queue? So we've got a couple things going on here. One of them is harder than the other. We've got a shift, right? Shift's not so bad. I could say shift the queue to the right. That's okay. What's my other option for this queue? How else am I changing this queue? What's the second? We see other assignments here, right? Queue of counts set to data in. So that's a little bit trickier. Has anybody thought about how we can incorporate that into our data path? How do we make sure we've got the appropriate wire selected? What's that going to look like? So count can be on the select bit of a mux, and then, well, let's see. Let's finish this. There's my shift taken care of. So count on the select bit of a mux, and then what's going into that mux?
Q is going into mux, but Q divided up into
16 different bits. And
So
so we'll be,
let's not draw that.
yeah. So we'll be selecting, we'll use, well, so we, so actually, I'm not sure actually that what's the conclusion? So we have count controlling a mux. That's going to choose the bit that we're changing, right? So then how do we incorporate the remaining bits? How do we incorporate the remaining bits? The bit that we're changing is just going to be data in, right? The bit that we're changing is just data in. So what does using a mux to select a bit do for us? We could think of things slightly differently, right? We could think of things slightly differently. We have a new tool at our disposal that we didn't have when we did the stack. What do we have at our disposal now that we didn't have when we had the stack that might help us out? A register file? We could, or tri-state buffers? Yeah, either one I think could be appropriate. So we have a register file now that, what if we, or this idea of using a decoder to choose what bit we're changing, right? This idea of using a decoder to select the bit that we want to write to. So we could imagine this, instead of being a register, perhaps being 16 one-bit registers, we use count as an address to choose the bit that we want to change, and then we just feed in a new value. Right? That was just a decoder. I don't have room to draw it on the board, unfortunately. But if you wanted to represent that here, what would you need to do? I could say address, right? I can add an address input. We've talked about that now, so that's legit. That's cool. We can do that now. Load acts as a write enable, basically. right? A write enable bit. So count now is going to select my address of the value that's going to be changed, right? For this particular guy, and then I can write in data in if I want to. I can write in the shifted bits if I want to, right? So that's how we can get around that particular problem. We are out of time. I am going to post solutions to this problem. I do have a few minutes if you have questions. You want to stick around after class, I can help you out. Otherwise, I will see you guys at the final exam, or I'll have office hours between now and then as well, so I might see you there.
So are you effectively making out of the
By the way, when I did this,
Yeah.
we're going to change something. One week,
Yeah, but really, we only care about the right
16
part.
into 16 bit, and just manually modify one of those break apart 02, then you get 16. That would be immediate.
There's actually a simpler way. This is actually, unfortunately, yeah, this is actually more complicated than it is. So I might recommend taking a look at I'll definitely make it clear what I want. Chances are, though,
Actually, I was going to say you were might be, I'd be selecting data, but I actually made it because of register, because
because otherwise,
then it's 16 file, 1 bit per file. Yeah, it's only slightly smaller.
it'll save you some time.
This is more
I'm not sure I understand. Reset takes precedence over everything. Reset versus write, reset never. Oh no, I meant like
yeah.
or that specific register. Reset. I was talking about reset should be.
So you basically give it an additional 16 to input and just say, oh, right, everything loaded at the same time. Okay, yeah.
I'm still not sure I understand. Maybe before register. Yeah.
It's hard to do a circuit diagram. Like if you got some variable that you want to reset, and you're reading it out here, rather than having it reset after the register, so that it just goes back and making it reset, having it before the register, so that it'll reset the value, but it will be
Oh, yeah, that sounds right. Because everything should happen on the right edge, even the reset.
Yeah, so the reset's always just before the register, right?
Yes. I mean, the traditional way to do a reset would be I'd have a mux, and one of them is just whatever zeros or whatever, and then one of my select bits would be used to choose. Reset would be one of my select bits to choose this value whenever I need it. So, and then this would feed into my register. Oh, right. Yeah, that's what I had. So if I was drawing a data path that had a reset, that's how I would do it.
Oh, okay, yeah, when I was drawing, I wasn't sure if it would be like the way you have it, or if you have to reset it. So,
No, this is the way.
okay, yeah.
And then the other.
Hey, just want to say thanks for teaching us.
I got it. What? I can't hear you. I'm sorry.
Like in the bottom of the box.
Uh-huh. Well, eventually they will be attached, and at that point you have to give them names, right? But until you're ready to do that part, you can just label them FSO. Does that make sense? I will make sure on the exam you know exactly what I'm looking for. I will spell it out explicitly. So maybe yes, maybe no. Yes? Oh yeah, thanks so much, man.
Yeah.
Appreciate it.
Appreciate it a lot. Did a pretty good job.
Oh, thanks.
Like that.
Thanks, man.
I just finished like my last little.
Good luck on finals, guys.
Thank
you.
See you later.
We'll leave it.
Whatever.
Oh, what? I'm gonna talk.
Probably.
Forget something?
Urine.